So let's talk about liquid-liquid miscibility and how that's illustrated on a phase diagram. The lines on the phase diagram are always equilibrium lines, and so they are boundaries at which multiple phases are in equilibrium with each other, sometimes two, sometimes more, depending on the complexity of the diagram and where you are on it. But in a liquid-liquid phase diagram, you can think of the lab experiment. That's the context in which we're considering this. And so this is all temperature. And it's temperature, and again, in a binary phase diagram, instead of having a temperature pressure map, we have one of the variables, temperature or pressure, and we always plot against composition. And so we'll make that 0 to 1. I'm always using A, you can use B, doesn't matter, so long as everything else is goes according to what you've labeled. So when liquids are miscible in all proportions, there's nothing really to illustrate. But if the ideal solutions don't have much here. But in these real solutions that we've looked at in the lab, for example, they manifest two different types of behavior, and sometimes at the same time they manifest this immiscibility or this phase separation, and it can look like it has a maximum or a minimum. And so let's start with one that you're familiar with from the lab. And the thing about these empirical illustrations is that it really can be what you want. So I like to stress that it doesn't have to be symmetrical. And so that's why it doesn't look so perfect. Clearly this is a maximum in the temperature, and so again, not labeling that point, but I'm labeling this temperature, and this is the upper critical solution temperature, or UCST. All right, looks like the name of a university. University of blah blah blah. This is my upper critical solution temperature. If that's my upper critical, then that tells me that the rest of the points that make up this line are all critical temperatures. And indeed, you collected some of those points and kind of sketched your best fit line through them. Your best imagined fit line through them, I think. I think what I'm going to do here is to separate my label from my actual curve, because my UCST label looked like an extrapolation there. So what is it critical to? It's critical to the phenomenon of phase separation. And so when you have a UCST, what that is defining for you is a two-phase and a single-phase region. This is my two-phase region, and the two phases are two liquids. Yes, you can say two liquids. I like to say two solutions because by definition that solution is a single phase. And so I have two solutions here that exist, and so I'll just draw it in here the way that it would look in a test tube after I let it settle. There's my solution, but in fact it's two solutions. So I have an air-liquid meniscus and a liquid-liquid meniscus. A meniscus is just a border between these two phases. My equilibrium line, and then this is all single phase region. So in other words, when I reach a high enough temperature, that goes away and it all goes into solution, as we say. So what I'd like you to be able to do is to be directed to a starting point, heated up with some labels and an explanation, maybe, of what's going on at each of these points in that direction. And remember, each of these are points, and so they have temperatures associated with them. So if this is called R, S, P, and Q, then this is temperature of R and temperature of S and temperature at P and temperature at Q. And you want to, using labels is really good so that you can write a paragraph and actually have something to refer to. So let's begin. I have in a test tube initially at a temperature R, I've mixed this much of ratio of A and the rest of B together. Are they miscible? Remember, you want to be using very precise vocabulary here. Sorry, I didn't realize you couldn't see that. There we are. Precise vocabulary. So it is an immiscible solution at temperature TR. Upon heating, well, let's stay at R for a second. So what is the composition of these two solutions? What is the composition? So you're thinking, well, isn't that the composition? Well, this represents the overall ratio of A and B in the test tube. So that's the composition of the mixture overall. But the mixture is made up of this guy and that guy. So what is the composition of each mixture? Can you tell? I'm at R. Okay, so at R, I'm in the two-phase region, and anywhere in the two-phase region, I can draw a tie line that extends to here, a nice, wonderful, horizontally straight line, and here. So you stop when you hit the equilibrium line. And when you do, you drop down, and this is the concentration, or no, sorry, this is the composition of the B-rich solution, and this is the composition of the A-rich solution. Isn't that neat? So I'm going to call this R1. Is that okay? And R2. Okay. So this is R1, and this is R2. There's no right or wrong which is which. Now what happens as I heat R? As I heat R, what's going on? I'm not adding anything else into the flask, but the compositions of the two solutions are changing. This is a real traffic area across the meniscus. So as I'm simply heating it, and if you watch it carefully, maybe the meniscus is moving around. As I heat it, let's get to S. So at S, I have a solution now that's S1, and the other solution that it is immiscible with is S2. And I keep on heating until I get to point P. And at point P, or at temperature P, this is a critical temperature. Okay? So in your paragraph, Whoops, let's, oh, things turning off. Oh, the wire's falling down. Oh dear. Okay. At that temperature, P, that is the critical solution temperature. It's not the upper critical, it's just the critical solution temperature. So that is the temperature at which I get phase separation for a mixture that has an overall composition of this guy. Okay? So let me reword that because I'm heating, so I'm emerging out of a two-phase region. So really this is, again, the critical solution temperature for a mixture of this composition, but in the direction I'm heading, it is actually, it's critical to the event that two phases become one. If I were cooling, it would be critical to phase separation, but here it's actually critical to coalescing. And heating past P, I have one phase, one liquid phase, a solution, and it's clear. There's only the air liquid meniscus left. So you could say that there is only one density now for the whole, throughout the mixture, throughout the solution. Whereas inside my two-phase region, I always had two liquids that were not miscible. You see? Two liquids. And they had different densities, which is why one floats on top of the other. And their compositions are always defined by dropping perpendiculars from my tie line intersections with the equilibrium line. It's neat, isn't it? A lower critical solution temperature is one where the diagram looks, like that. And you have a lower, so basically the mirror image. And your textbook shows you where some have a min and a max, which is very cool because you start as a one-phase liquid, and as you heat it, it phase separates, but as you continue to heat it more, it goes back into one. It's very neat. Okay, I think what I want to show you next is what happens when we move horizontally across this phase diagram.